Hi, today we have a project which I've been meaning to do for quite a long time now, all the way back when I did the medical isolation transformer project. So I purchased this Variac from eBay, and in transit it appeared to have been damaged, so I think it had got dropped in its box. It wasn't very well packaged, and this is a bracket which holds the Variac core together and to the chassis, and you can see it's sheared along here, and there were a few other breaks here, and this was basically all bent out of shape. The Variac knob was at about 30 degrees to the rest of it, and it wasn't really working properly. So big thanks to Tony at Carrol Maynell. He sent me a replacement bracket absolutely free of charge, so that's absolutely superb. I was going to try and just live with the glued together part, but now we've got a new part, so that's great. So we'll be able to assemble the Variac back together as it was. And then the other problem is that the Inrush current for this core was quite high, and occasionally it was tripping the 32 amp B-curve MCB in the fuse box. So what I want to do is build a soft start circuit. So I've got a PCB which I had made quite a while ago. It's slightly overkill, it's got a few extra features, but we're going to build up this soft start circuit so that we hopefully don't trip the MCB every time we turn it on. And then we've got a couple of contactors for turning it on and off and switching in the resistors. I've got a 13 amp metal clad double socket, the same as what I used on the medical isolation transformer, so we can plug in devices that already have a 13 amp plug on it. And this particular model came with a quick test connector, so you can just insert bare leads, which is fine for some devices, but obviously if you just want to control a lamp or something like that that already has a plug on it, really we want a 13 amp socket on there. So we'll have a quick look at the soft start circuitry first. We'll build that up and see if we can get that working, and then we'll try and work out how we're going to get all of this into the box. Hopefully it'll all fit. These contactors are slightly bigger than I thought they might have been actually, so the base is quite chunky. Hopefully they'll fit in the front here, otherwise I'll have to order a pair of different ones and wait for those to arrive to complete the project. So here we have the schematic for the electronics which I've implemented on this PCB, and what we're trying to do is limit the inrush current to the Variac core. So the Variac core basically acts like a big inductor, and when you first turn it on, there's a very high inrush current because basically it has a very low impedance, and then as the core magnetizes, the impedance increases. So there's lots of ways which you can limit the inrush current to the Variac, and I've chosen a very simple one. So basically we're going to limit the inrush current just by using quite a large resistor. So this is a 220 ohm resistor. It's actually a 100 watt power resistor. The continuous load, if this was into a short circuit, this resistor wouldn't be able to dissipate all of that, but we're only going to switch in this resistor for half a second or so. So basically this is wired in series with the coil, and then after half a second there's a contactor which shorts this resistor out, and then it allows the full current to the Variac. So we've not got anything complicated in the electronics. So we've got a standard linear power supply here. So we've got a transformer input here, 9 volt AC, into a bridge rectifier, and then a reasonably large bulk storage capacitor. And this is what supplies power to the contactors. And then we've got a resistor here just to drop a little bit of voltage so we're not dissipating too much in the regulator. Some more capacitors around that, and then that's our 3.3 volt supply to the microcontroller. And then we've got a couple of drivers here for the contactors. So these are standard open collector NPN transistors on each of these, with a back EMF protection diode for the relay, and then also a couple of LEDs just for indicators on the PCB. Then we have the in-circuit programming header for the microcontroller, so that's just a standard 5-pin header. And then we have the microcontroller itself. This is a PIC 18F13K22, and this is a nice little 20-pin SSOP packaged microcontroller, and that just has an RGB LED attached to it for status, and then a couple of capacitors here, and the rest are inputs and outputs. And then I've also implemented a bit of circuitry so we can have a stop button, and this is just to turn the power to the sockets on and off, but also when you first turn it on you have to reset this switch first, so that if you had something attached to it and you accidentally had the voltage up at maximum, you don't blow it up. And then finally, just an additional bit of circuitry here, just so that you can turn the outputs on and off remotely. So we'll have a 4-pin connector or something on the back of the Variac, and once you plug in the connector, it turns this enable input low, and then basically you can turn the output on and off by supplying power to the top 2 lines here, which go through a bridge rectifier just so that you don't have to worry about polarity, and then through an opto-isolator so that the circuits are completely isolated. And then for the PCB, it's just a standard 1.6mm double-sided board, which I had made at Elecro in China. That's the same place I had the GPS disciplined oscillator board manufactured. And this has got the power supply section here, so we've got the input from the transformer, the dropper resistor here, some capacitors, and then the regulator and the bridge rectifier. We've got the section here for the external trigger, and this is where the opto-isolator goes. Then we've got the stop button input, the outputs to the 2 relays and the reload drivers, the PIC microcontroller, the RGB LED, and then the programming header. So that's all fairly straightforward. It's a nice little compact board. So what I'm going to do now is assemble that with all of the components, and then we'll check that it works. Okay, so here we have the completed PCB. I didn't bother filming it. I wanted to get this done fairly quickly, and there's nothing too complex on here. So you can see we've got all of the terminal blocks for the external connections. You can see we've got the relay drivers here, so the little transistors, some indicator LEDs just for debugging purposes, and the back EMF protection diodes. You can see we've got the SSOP microcontroller here. That was fairly straightforward to solder down. I didn't put the LED in. I don't know whether this is going to be mounted directly to the panel where the LED is going to be or not, so just in case it's mounted remotely, I didn't bother fitting it. Then we've got the 5-pin programming header. We've got a couple of Panasonic FM and FC capacitors. I always like using these. They're really good quality. Even on something basic like this, it's worthwhile. We've got the voltage regulator and some little capacitors here. Surface mount bridge rectifiers and the opto-isolator. And then we've got the resistor here for just dissipating a bit of power, so we're not dissipating all of the power in the SOT223 package here. So what we'll do now is we'll program this up and just check it all works correctly. Hopefully the code works. I've simulated it in MPLab and it all seemed to work correctly, so it should just be a case of flashing it onto here, and we should be in business. So here we are in MPLab, and this is the firmware for the microcontroller on the soft start board. And this is a really simple bit of firmware. It's not doing anything complex. So here we just set up the oscillator. I've arbitrarily chosen 1 MHz. It doesn't need to be as fast as that for something as simple as this. And then we just set up the GPIOs. So we've got the inputs here for the button and the external trigger, etc. We've got the 3 outputs for the LEDs. And then we've got the 2 outputs for the relays. And then we've just disabled all of the interrupts. The watchdog timer is enabled, so at this point we just clear the watchdog timer. And then after that, so this is the first bit of real code that gets executed, and the timer 1 here is configured for a 500 millisecond delay. So when the microcontroller first starts up, the contactor is open, so all of the current into the Variac is passing through that power resistor. And then after 500 milliseconds, we short out that resistor, and then the full mains current is available to the Variac. And then again, we just clear the watchdog timer. This is the point where the relay is actually turned on. So here we have a little bit of code which is just making sure that the output isn't turned on accidentally. So if the stop button was previously in the on position, then just to make sure that you didn't accidentally put the wrong voltage out on the Variac, you have to actually physically push the stop button and then release it again before the output's enabled, and then we turn the LED on to green just to say that the Variac's ready. And then there's a little delay here just to let everything settle. And then here we have the main loop. So after doing the initialization routine, we've got 2 blocks of code in the main loop. So this first section of code is when the external trigger mode is turned off. So when that external trigger mode is turned off, the device just operates as normal. So if the emergency stop is pressed, then the output relay is turned off and there's no output from the sockets. And if the emergency stop button is released, then we get an output, the output relay is turned on and the output of the Variac is connected to the socket. Then we have a second bit of code here, and when the external trigger mode is enabled, we reflect that mode with the LED turned to blue, and basically the output follows the input. So the stop button's still active, so if the emergency stop is depressed, there's no output from these sockets, but otherwise, if there's an external trigger not there, then the relay output's turned off, and vice versa. Right, so I've just attached some wires to the PCB, and I've got 12 volts on the output from my DC power supply, which should be sufficient to power the device. Obviously a 9 volt AC input then gets rectified and then regulated, so it's probably the equivalent of close to 12 volts, but the regulator can handle all of that. So we'll apply, the plout is correct, so if we connect 12 volts, and we're not drawing any abnormal power, so there's no dead shorts or anything like that. I set the current limit to about 20 milliamps, and it's drawing less than 1 milliamp at the moment. That's good. So I'll attach the PIC kit 3, which we're using today, into the board, and we should just be able to go ahead and program the device in MPLAB. So I'll click Program, and it's detected the device programming, and it's completed programming. So it seems to be able to communicate with the micro properly, and we've got one of the LEDs lit here. So this is the output to the soft start relay, and this is the output to the relay which turns the power on and off to the socket. So you can see now this relay is energized. If we disconnect power, when we reconnect the power, you should see a delay of about half a second or so between applying power and that LED coming on. So I'm applying power now. So that's working correctly. We're emulating the stop button with a wire here, and the way that these emergency stop buttons work is when you push them, it should be off, and when you release, the output's on. But the switch contacts are obviously inverted, so when you push this, you make the contacts, and when you release it, you disconnect it. So normally, with the switch pushed down, which is in the off position, this wire would be shorted out. So if we apply power, you should see we've just got the soft start relay energized, and then if we were to do the equivalent of releasing this switch, which is releasing this wire, we got the output turned on here. And I've got one of the RGB LEDs which I'm planning on using, so I should be able to push this into the pads here. So if we apply power again, it's correctly working here. And it has the protection working there to make sure the output's not accidentally on when you turn the power on. I'm assuming this is going to work. I'll test this offline, it's not particularly interesting. Right, so now the electronics is working, I'm going to try and work out how we can assemble this whole thing together. So I was going to mount the 13 amp socket to the front of the device, how I did on the medical isolation transformer. So I was going to cut out around here and mount this flush to the front panel, but I don't think I'm going to have enough space in here. I think I'll have to use the metal clad patras which matches the socket and mount this surface mount on the front of the Variac. And the main reason is that these contactors are quite large, so I think these are going to have to mount to the front of the unit like this. I could mount them on the base, but I don't really want wires going between the two halves of the casework, so I think this is going to mount to the front here. And also the mains transformer is excessively large. Unfortunately the 6VA version was out of stock, so I had to go with the 12, which is a little bit chunkier than I'd like. So this will probably also have to mount to the front unless there's a little bit of space at the back here. So after that, we've got the power resistor, which can mount really anywhere that's available, probably at the back just here. And then the PCB can go also anywhere that's available. I'm kind of thinking that it will fit up here with the indicator LED either on the front or on the top. So it looks like everything should fit in. So what I'm going to do is I'm just going to have a play around. There's also the emergency stop button again, which will either go here or here. And once I've worked out where everything's going to go, I'll drill all the holes and then I'll rejoin you after I've done that. Right, so I've drilled all of the holes for all of the various components in the Variac case. It turned out that the standard EI core transformer was just too large to fit in the case. I couldn't find anywhere for it. So I ended up ordering a toroidal transformer from RS, and this seems to tuck in nicely just down here at the bottom. It's worth mentioning that if you do buy one of these toroidal transformers from RS, it doesn't come with any of the mounting hardware. So you have to order the washers and the various bits separately, which is a little bit annoying, as this did arrive just bare, and I had to order those parts again separately. The 13 amp socket mounting holes, I'm using these two here, which correspond to these two holes in the Variac case, look like they can be used to mount the contactors as well. So the two contactors will sit here and here, and that just about clears the wiper on the Variac core. It's worth mentioning that this wiper is the whole metal object here becomes live once the Variac is energized, so you don't want anything coming into contact with this wiper here. And when it comes to wiring up the Variac itself, there's 5 connections on the side of the Variac on this plate here, which is mounted to the Variac core. And the Variac is a type of auto transformer, so there's a series of windings around the core, but there's no secondary winding for the output. The output is taken between the common neutral connection and some point between there and the end of the transformer windings. So the incoming mains connection on this model can be between terminal blocks A and D or A and C. So if the incoming mains was between A and C, the output could simply be between 0 and 240 volts. If you connect your incoming mains connection between A and D, you get 0 to 240 volts at this point, and then you can exceed the incoming mains voltage up to about 270 volts from between C and D. And then here's a little bit of detail on the transformer itself. So there's lots of enamelled copper wires wound around the core, but this is ground down along the top here, and then there's a metal brush which, when this is seated in place, comes into contact with the top here and makes contact with the windings. And I think I've mentioned it in a video before, but whenever you're using these crimp terminals, make sure you use a good set of ratchet crimpers. The cheap crimpers that come with these sets that you can buy from the pound shop and stuff are awful. So I'm using these Pressmaster crimps. They've got quite a long handle, so you can get a lot of force on here. And when you open them up, you can see the jaws, especially indented for these types of crimps, and they fit in one way round, so you can see this is where the cord strain relief is, and on the other side is where it actually makes contact with the crimp. So you can just close those slightly and insert the cable. And then you can hear the ratchet mechanism as I squeeze the jaws. And then just visually inspect the crimp once you're done and give it a quick test to make sure that it's not falling out. And that's a correctly made crimp terminal. And also always make sure that you're using the correct size crimp terminal. So you'll see the jaws on here are colour coded red, blue and yellow. Red is for cables up to 1.5mm squared, blue for up to 2.5mm squared, and then we've got the yellow here which is up to 6mm squared. So red is the correct size for here. Also make sure you've trimmed off the correct amount of copper. So when you push this into the terminal, you should just see a little bit exposed, and then you can crimp your crimp up properly. And you should just see it flare out the end slightly, and you can see that the bottom section of the crimp here is providing some strain relief on the actual wire itself. Right, so I've finally assembled everything back together again. It was a little bit close here between the PCB and this relay, and it is actually just sitting on this board slightly, but it doesn't seem to be causing any problems. I must have just measured slightly incorrectly, but everything seems to have fitted in. These contactors themselves were 3-pole changeover relays, and each contact was 10 amps. So what I ended up doing is paralleling all 3 contacts up to increase the current handling capability up to 30 amps, just in case the Variac was ever overloaded when we're doing some fun tests later on. I managed to squeeze in the transformer at the back here for the PCB here, and then there's the power relay at the back of the Variac as well, but everything seems to fit in there. So the next thing that we need to do is start running some tests before we power it up with the mains. So the first test that we're going to perform on the Variac is with this digital insulation and continuity tester, and we're first of all just going to check that we've got a good earth connection to the chassis of the Variac. So I've got a 13 amp plug that's wired onto the mains lead for this. I'll attach one of the crocodile clips to the earth pin here, and then find a suitable point on the chassis, which is metallic and not painted, so this connector at the back should be fine. And then if we turn this on and set it to continuity and press test, you can see we've got good continuity between the earth pin and the chassis, and this actually runs quite a reasonable current through the test leads to give us a good low reading. Although I didn't bother nulling out the leads, you can see that we've got a good reading. The next thing we want to do is just make sure that we haven't got a dead short between the phase and neutral connections when we plug it in, so it just doesn't go bang. So I'm going to attach the leads between the phase and neutral connections on the plug and click test. And we've got 113 ohms, so that's with the main switch on. We can do it with the main switch off, and it's infinite. Press test again, and so what we're seeing here is the parallel combination of the Variac core and the 200 ohm resistor in series in parallel with the little transformer here for powering the logic board. So that all seems quite reasonable. The next thing we want to do is just check the insulation. So to test the insulation, what I'm going to do is literally just connect the crocodile clips between any of the line pins. So I'm going to attach it to both the neutral and phase pins, and then the other one to the earth pin. So this is checking that we've got a good high resistance between the chassis or earth and anything else in the Variac. So I'll set this to the insulation test, and we'll do a 500 volt test and click test. And you can see we've got basically infinite resistance there between any part that would come live and the safety earth. So I'm quite happy that this is all wired up correctly. The basic tests that I've just done there just show that this is safe to connect up to the mains. So what I'm going to do now is just plug it in and see if it works. So just being mindful that most of this is going to become live, including this bit on the Variac here, I'm now going to turn on the power to the Variac. And then we can turn on the power switch, and we should see the contactor on the left here energize after about half a second, so that's a soft start relay. And then this one shouldn't turn on at all because the emergency stop button on the front hasn't been cycled. So I'll turn this on now, and we can see that's clicked in. We've got the LED on the PCB, which you may just be able to see. It might be slightly obscured by these connector blocks. And then if I cycle this emergency stop button, you can see that relay there just clicked in, and we should now have an output on the sockets on the front. So here we have the fully assembled unit. We've got the mains lead at the back here. This is some 2.5mm squared 3-core rubber flex. We've got the interface here so that we can remotely turn on and off the output relay, and then obviously the power switch. And then at the front of the unit we've got the 13 amp socket for devices that already have a BS1363 plug on it, or the quick test connector for inserting wires just into the Variac without a connector. We've got the emergency stop button here, which you push down to activate, and then twist and release to turn the output back on. The indicator LED at the front, and then obviously on the top we've got the knob to vary the output voltage. So what we can do now is just plug everything in and just test that it actually does what we expect. Right, so for this test we're going to be using another device from Socket and C. This is a non-trip loop tester, but it can be used just to quickly check that you've connected up your sockets correctly. It doesn't indicate every fault possible, but it does give a quick indication on the front whether you've connected everything, you know, whether you've got the polarity correct and the earth is at the right pin and that kind of thing. And it also shows the voltage on the front. I'm not sure at what voltage this will start working. It's got no internal battery. So it might be until this reaches 50 volts or something we start to get an output. So I'll turn on the Variac. And the dial's at 0. We've got the green light so we can just release the stop button. And now we've got the turquoise light so we can increase the dial here. And it's starting to do something there. It's not quite enough. It's working at about 60 volts. 80. And we'll start increasing the dial. I'll only take this up to 250 volts, I'm not sure what this device is rated for. But you can see that seems to be reading correctly, and the 3 green LEDs on the front just mean that it's wired up correctly. And we can also repeat this test with the Fluke 179, this should be a lot more accurate. I've just poked this into the quick test connector so we should see the voltage here. So I'll start winding up the wick. So that's at about 10 on the dial, it's reading 11 volts. And that's 55 on the dial and it's reading 55 exactly. That should be about 150, which it is. That's about 240 volts, and then if we whack it all the way up to the max, it's reading about 264 volts. So that seems to be working correctly. Finally we can just test it with an actual load and just make sure that it works correctly under load. So about the only thing I can find at the moment that I can plug in is this very crude ozone generator which I made. The idea was that there's a fan at one end, there's 2 pieces of mesh and an acrylic tube. This is an 11,000 volt transformer, and you just push the air through and it fills the room with ozone. You might be able to hear it on the microphone as I ramp it up. We'll have a go. And I guess we may as well just draw a little arc since I haven't used this in ages and it probably needs rebuilding anyway. And finally we've got the power meter powering the Variac, and what we're going to do is have a look at the inrush current on the Variac just to make sure that the inrush current is now limited. So we'll pan up to the scope. Right, so we've set up the oscilloscope for 1 amp per division being drawn from the main supply. It's set onto single shot capture, so I'll just turn on the Variac and we should see what happens to the current being drawn from the mains. And there we go, we've got a little negative spike here, but then we've got a positive spike, so it does depend at what point you turn it on the AC waveform, but you can see both of those less than 2 amps, so the soft start circuitry is doing exactly as it should, and there should be no risk of it tripping the 32 amp breaker in the fuse box now. So I hope you enjoyed that video. Apologies if it's a little bit long-winded. It was recorded over quite a few recording sessions, mainly because time's been very sparse because this one was born back in September. So this is Camden. Obviously the Variac is massively overkill. You don't really need all of that functionality and there's a lot you could do to reduce the costs, but since it's a one-off I figured I may as well just go all out on that. In the next video or two we're going to have a look at this light which we bought for Camden's nursery. This is a China special, so there's probably some nice surprises inside. And also the GPS unit's got another problem, so we're going to also have a look at that. But anyway, I hope you enjoyed this video. Please give a thumbs up if you did. If you didn't, give it a thumbs down. Subscribe if you haven't already. And thanks for watching.